Okay, so limits. What's a limit? Describe what it means if we say something like as x approaches a value, the limit is something.
It's what's expected to be.
Yeah, right, what's anticipated. Does it matter what actually happens when you get there?
No.
No, not insofar as the limit is concerned, right? Okay. What else has to be true for a regular limit, like we're talking about now, to exist? We had an example where the limit didn't exist. For example, you told me at -1, there was no limit. How come?
There's two possible.
Okay, so,
Different from each direction.
okay, right, it was different from each direction. Okay, so we said that's a kind of a place where limits don't exist, right? Limits, the ants approaching from left and right have to agree on what their destination is predicted to be, right? So breaking the function, limits don't work. We had just started talking about a different kind, right? Now this is one where ants from the left and the right could agree on the behavior of the function, right? But they could never agree on a place they were approaching because it doesn't exist, right, with an asymptote. As x approaches 1 in this case, what is the actual value? I mean, there isn't a value, but how could we describe what the function approaches?
No.
So we actually could, the answer is no limit, and that's the correct answer for now, because the limit's not defined there. But later on, we'll be a little more specific, and we could probably even say something more than just no limit. Sure, it's no limit, but no limit because of what? What is the function doing? As x approaches 1, f of x approaches what? You're going to say it, Michaela. I know you are. Infinity. Right? Okay. But that's not a limit. So the answer for now is just no limit. Okay? There's one other kind which is really bizarre. And there aren't very many examples of this. I think here's one that I believe would work if we did something like, let's take the function f of x equals sine of the quantity 1 over x. Okay? You don't see stuff like this very often, but it's kind of interesting. So what's going to happen there? Now this is a composition of functions, right? It's a function of a function. Okay, so the outside function, sine, is seeing output values of the inside function, 1 over x. There's 2 steps to this, right? I plug in values for x into the inside function. It spits out values that the sine function needs, right? So what's that graph going to look like? Let's compare it to, real quick, let's compare it to g of x equals sine x. Okay? So what's that look like?
Isn't it like
Yeah, just sine function is going to start at 0, right? And just go like that. What's its maximum y value?
1?
Minimum y value? Well, -1. Just like that, right? Okay, and we know that that's the way it is because that's what a sine function does. If I take the sine of pi, I'm going to get 0, right? Sine of pi halves, I'm going to get 1. Agreed? Okay, what's different about this one, though? The values it's being fed are going to be distorted by that inside function. So let's just plot a few points out about it. What's going to be the case when x is really big? What does sine look like? So if x is approaching infinity, what is that going to approach, do you think? We haven't talked about this yet, but if I get a really big number on the bottom of the fraction, what's the value of the fraction approach? really small. Okay, so if we go way out to the right then, we're gonna be effectively taking the sign of 0. What's the sign of 0? Sign of 0 is 0, isn't it, right? So this thing is going to kind of approach 0 out here, isn't it, right? On the way to 0, this is gonna change signs a whole bunch though, isn't it, right? Well, actually, hang on, no it's not. It's not. What if we pick a value, now in here it's gonna be different though, right? As x approaches infinity, this settles on an answer of 0, but there's a lot of numbers between infinity and let's say 0, okay? What if we pick a value like 1? Well, the sign of 1 is just some number. Sign of 1 is gonna be what? Something like that value, okay? We're gonna get some positive value. What if we pick a number like 2? Well, sign of 1/2 is gonna be a slightly smaller number, right? Does that make sense? So as we move further out there, this function is going to gradually approach 0, right? But when we start to back off and get closer, we get like inside of 1. What is 1 over 1/2? 2. What is 1 over, what's 1 over 2 over pi? Pi over 2, right? So 2 over pi is gonna be a little less than 1, does that make sense? So that's gonna give us a value there, right? What's 1 over 0.1? 10. What's 1 over 0.01? What's 1 over 0.001? Wow, what's going on? It's pretty boring out here, isn't it? This thing is gonna be, it's just gonna kind of do this kind of thing, but when we start to get inside 1, what's going on? Yeah, inside between 1 and 0, how many different numbers are between 1 and 0? Infinite number, right? And look what's happening to this function. As we back down towards 0, these numbers are just growing without end, aren't they? As x approaches 0, what is this value approaching? 1 over infinity, isn't it? Right? Does that make sense? Like 1 over 0.000001 is going to be some really big number, right? And so what's going to happen between kind of there and there? It's just going to oscillate wildly, isn't it? Right? It's just going to start doing this, and then it's just going to never stop because there's no boundary to the upper limit of that argument of sign. Does that make sense? We actually can't put 0 in there, can we? Because we can't divide by 0. So there's a hole in the function at 0, but as we approach 0, there is no value we ever can settle on because the smaller x gets, the faster this argument, the 1 over x, is growing. Does that make sense? So can we ever get a limit then? What is the limit of sine of 1 over x as x approaches 0? Well, who knows? The closer you get to 0, the more wildly this thing oscillates. It's never going to settle on a value, right? Okay. Isn't that weird? And it would do the same thing from the other side, right? It would just be negative. It would just look like this. So oscillating behavior is the third category of place where limits don't exist. You get weird stuff like that happening, where the function just gets really frenetic and it just oscillates more and more wildly. Okay.
So would you put one of those, what's it called, the holes at 0?
Yeah, you could. It'd be pretty hard to graph though, because you don't know. I mean, you can't even really draw the hole. See what I'm saying? Because you don't know where does the hole attach.
Do you ever get to the hole?
You would never get there, right? Because look over here. I mean, like in these cases, yeah, we can get to the hole in the function, right? But you could never get there. And you can look at it, there's interesting ways to look at math. If you look at it from kind of a whole different branch of mathematics would be topological math. And how long would how much ink would I have to use to draw this function? Yeah, so if the amount of ink I use is proportional to the amount, to the stretched length of the function, would you agree that the stretched length of this function is infinite? So could an ant, isn't it interesting? Could an ant ever get from there to the hole? It's impossible. You'd have to traverse an infinite amount of function, which is impossible to do, right? That's way above the scope of what the book talks about. Isn't that interesting though? Think about it that way?
That's
There it is,
crazy.
yeah, there it is, yeah.
Zoomed in 3 times.
Yeah. Show show everybody that, that's, yeah. Okay, so.
Yeah.
So let's see, so now, where are we here? Just want to kind of make sure I'm covering the stuff that's going to be on the homework.
We don't need to.
Oh, we don't need to bother with that.
Yeah, we got it.
Okay, so, actually, we're in, you guys are in pretty good shape for that. I wonder if I should throw out, no. No.
That's calculus. That's a whole.
Do you guys have your books with you?
Yeah.
Okay, grab your books real quick. I don't wanna have to write all this down, but we'll talk about, because we have some time, we'll talk about this today a little bit. I don't normally cover a lot of this with my calculus classes, but I'm going to with you guys. You guys are a small class, we can deal with this. So, take a quick look on page 51. We're going to talk about the formal definition of a limit for just a second. Okay, so maybe I should draw this. Okay, so if we've got, here's kind of the picture. Calculus is about pictures. A lot of times, a lot of the theorems and the relationships we deal with, I'll just call them picture theorems because a picture summarizes the whole thing. This is somewhat like that. So if we look at, let's say we've got some function f. And we're going to pick a value c that we want to approach. Okay? There might even be a hole in the function at x equals c. That's fine. We can deal with that. Okay? So here's what we want to do though. We want to describe a neighborhood of values, and that's the word we use in math. It's a friendly kind of a concept. It's a neighborhood of values with a width delta. Because oftentimes this is the Cauchy theorem is how this, or the Cauchy definition of a limit, but usually people just call it epsilon delta. There's the delta. So it's on both sides. So then this is going to be, this neighborhood of values around the x value that we're approaching is going to stretch from c, because that's what we're calling the value, minus delta up to c plus delta.
How do you determine delta?
Well, that's what we're gonna talk about. Delta is variable in a way. Okay? So we want to see if we can come up with a way of formalizing the working definition of a limit that we've already started using. And this is the one we'll always use. This is the convenient way to think of it. So we're gonna take the statement, the limit of f of x as x approaches c is L, okay? So that's my y value, L. And the picture makes sense. As an ant walks along this function, approaching c, as x value approaches c, the y value is approaching L, right? Okay? If we want to formalize that, we have to write this a little differently though. Here's the language of the book. And I want to kind of make some connections here. If x becomes arbitrarily close to a, if f of x, sorry, got x, whoops. There's some really good language in here I want you to get used to. If f of x becomes arbitrarily close to a single number, this is right out of the book, L, as, I'll just kind of encapsulate this, how about, as x approaches c from either side, comma, how do I do this here? Down a little bit. From either side, then we say that this is true, that the limit of f of x as x approaches c is L. Okay.
What does arbitrarily mean?
Yeah, that's a key word though. If f of x becomes arbitrarily close to a single number L as x approaches c. Arbitrarily is the key word in that whole statement. Hey Mitch? Good, what's up? Mm-hmm. Mm-hmm. Yeah, we do. We're either gonna buy it or I'll just set it up. I don't think so. We'll have to check, I don't know. We need to do that for sure. I'd ask Kim, I think she might know. Yeah. Yeah. Mm-hmm. I'll do that. I'll get all the accounts set up. Yeah, I can do that. Mm-hmm. Yeah, that'd work. Yeah, that'd work. Okay, sounds good. Uh-huh. Bye. Okay, sorry about that. So arbitrarily, key word. What's that mean?
Isn't it like, not ordinary?
Standard.
Kind of means, well,
Subject to individual will or judgment without restriction. Contingent solely upon his discretion.
yeah, well, there you go. So it's not pinned down, in other words, right? There's no limit to how close we could get, right? So if I get to, the point being that here's the point, if I want to get this close to C, then I should only expect to have a certain target accuracy with my limit, right? Agreed? What needs to happen for this limit to work? Wouldn't you agree that if I decide I want to get closer to hitting the target of L, what should I have to do? Get closer to C, right? See what I'm saying? So this wouldn't work though, would it? If, as I got closer and closer to C, the value of the function started to deviate from L. That would be a problem, wouldn't it? That wouldn't be the kind of limit behavior that we've been talking about, right? So the word arbitrarily is important here because we should be able to get as close as we want. It's arbitrary. It kind of depends on what our target accuracy is, right, so to speak. We should be able to get as close as we need to get by just to L by just simply approaching C with more precision, right? Getting closer to C. Yes?
By that logic, why wouldn't an asymptote have a limit at that point?
Well, it does. That's fine. If I understand you understand your question, you're saying something like this. We haven't really talked about infinite limits yet, but we'll get there. But you're saying, correct me if I'm wrong, what you're saying is, for example, you want a vertical asymptote or a horizontal asymptote? Doesn't matter. Okay, so let's make it a horizontal asymptote. And how about at 2? What if my function does this? What if my function goes something like that, right? Okay, so in this case, we would say that the limit of f of x, we'll call that, as x approaches positive infinity is 2, right? So what do I have to do in this case to get closer to my target y value of 2?
Closer to just keep on going down the line.
Exactly. Go further to the right. Every step I take to the right is going to get me closer to my target. That's okay. That matches this kind of behavior, doesn't it? Same idea.
But you'll never be able to hit that.
I'll never be able to hit it, but I never hit it here either, right? It doesn't matter if there's a hole in the function. This matches the definition of a limit. It works as a limit if I can always guarantee that I'm going to get closer to L, as close as I want to get, by just getting my x value closer to C. See what I'm saying? Where would that fail to work? Well, what if our function, I'm just going to draw over the top of this and then I'll erase it because it's going to look messy. What if my function didn't look like this? What if my function looked like this? It's going to be the pink one now instead. Or purple, sorry. What if it did something like that? That doesn't work, does it? Because now there's no way for me to get close to a single value of L by just more closely approaching C, is there? See what I'm saying? Right?
So what would you say the limit is?
It doesn't exist, right? Because we can't do this. It doesn't work.
So on the one with the asymptote, why can't you just say that arbitrarily, if you went right a couple more feet from our perspective, just say arbitrarily that's close enough for that y or x value to be the limit?
Sure, could be. What if you only needed to get that close? Well, then you only have to go that far, right? But that shouldn't be the stopping point. It's arbitrary. We should say, well, okay, it turns out I want to go 10 times closer. I can do that. I can get 10 times closer to my limit by just going some distance further to the right.
Yeah,
But that,
arbitrarily, you can pick a spot, but at the same time, you still have to acknowledge there's more there.
but, so it'd still be the right answer.
Well, sure. So, yeah, think about it in terms of a real world application. Let's go back for a second to this one. I'm going to get rid of the purple. So let's just say that we're machining apart a ball bearing or something, right? And we're going to control the radius, and that's gonna relate to the mass of the ball bearing, okay? If we need the mass to be within a certain tolerance, right? What if we only need the mass to be within plus or minus 1,000th of a gram or something, right? Well, then we ought to be able to do that by getting our radius accurate to a certain point, right? To a certain distance, certain length. In the future, though, I mean, shouldn't be a limit to that, though. What if we needed it to be accurate to 1/1,000,000th of a gram? If we needed it to be accurate to 1/1,000,000th of a gram, then in order for the relationship that connects radius to mass to work as a limit, all we should really have to do is just control the radius more tightly, that tolerance more tightly, right? There can't be a breakdown, though. For a limit concept to work, we can never run into a situation where I can't get closer to my desired value by simply narrowing the width of the neighborhood. See what I'm saying? Okay? So it's really a highly conceptual thing, but I honestly think that you probably all get it, in the sense that this only works if the limiting behavior is exhibited. By walking closer to a certain X value, you're always going to get closer to the corresponding limiting Y value, okay? This is a little more difficult to prove. I don't know if I'll assign anything like this or not, but let's just take a look at a couple examples. Like, I'll just pick some problems out of the book here. What if we wanted to, for example, look in your book at problem 21. Okay, this would be good to look at. Yeah, I think this'll, I like this. I'm glad we're doing this. Okay, so find the limit L. Okay, then find the value of delta non-zero value, right? Such that the absolute value of f of x minus L is less than 0.01 whenever the absolute value of x minus c is less than delta. Okay? When we talk about an absolute value like that, what does that represent? What does the absolute value of f of x minus L represent? What's positive, but it's just a distance, right? A distance between those values, okay? So here's our function for this one. Our function is, okay, 21 we're doing, so this is the limit of 3x plus 2 as x approaches 2. Okay. Well, L is just the value of the limit. What is it? We don't even have to graph it, do we, really, if this is what we'll come to call direct evaluation. But if I were to graph this, are there any holes or bizarre things? No, it's just a line, right? So on that line, as x approaches 2, the ant is going to be approaching what y value? Well, whatever the y value that the function actually has is the value he's approaching, right? So what's it going to be? 8, right? 3 times 2 plus 2, right? So that's, whoops. So L equals 8. Okay, we got that. But now what if we want the distance between the function and the limit, right, to be less than 0.01? What's going to have to happen? How are we going to, what's that going to mean about the relationship between x and c? How close are we going to have to get? How are you going to do that?
Has to be at least 2.
Say it again.
At least 2. So if you plug the 2 into the thing, and it gives you 0.
Okay, well, let's. How are we going to approach this, right? If we know that this quantity has to be less than 0.01, we want to just. Our goal is to start here, and we want to come up with some kind of inequality that's going to give us the value of delta, right? What is c in this case? based on our limit? 2, right? C is the value we're approaching. What is L? 8, okay? And this is really epsilon, isn't it? Right? If we go back to our, did I ever write it in terms of epsilon? I don't think I did. Oh, I meant to. Whoops, forgot something. So the width of the neighborhood of x values we call 2 times delta, right? The corresponding width of the output values we label epsilon. So this is going to be, this is epsilon, and that's epsilon. And so this upper y value is L plus epsilon, and the lower value is L minus epsilon, right? So really, well, my only point in doing that is just to show you that we're just defining how tightly we want to get to that limit, right? How tightly do we want to approach that y value? So, oh, what did I just do? Deleted. Did I delete everything? I'm going to be really ticked, but I think I just accidentally did.
Oh.
That is so bad that I can't even tell you. Yeah, I'm recording. Oh, man.
Did you?
Oh, no, I didn't. No, I didn't. It's right there. Ha! That's what I did. Nice. Scared. Okay, so right, that's all we're saying is that the distance between the actual function and L has to be less than or equal to 0.1. So wherever we are on the function, right? Like if we're right here, for example, well then we need to be within points, was it 0.01 of our target value L, right? Okay, so all we got to do then is just take this expression and fill in the blanks and do some algebra and try to get an outcome like that. So what is f of x?
3x plus 2.
3x plus 2. So this is going to become the absolute value of 3x plus 2 minus 8 has to be less than 0.01. Well, do some algebra. What do we get? If I simplify this, I got to work inside the grouping symbols, right? So what's 3x plus 2 minus 8?
So x would still be 2? Or, no, it's not 2.
So 3x minus 6 would be step 1, right? So the absolute value, all this stuff just becomes 3x minus 6 is less than 0.01, right? What do I do now to solve for x? Okay, good. I got to factor out of 3, right? So we'll make this, and I'm going to show these steps. This is a step we could skip probably. I could rewrite that as 3 times x minus 2, right? But then if I break that apart into the absolute value of 3 times the absolute value of x minus 2, what's the absolute value of 3? 3. So does it make sense that I can just pull that outside algebraically? Okay. So we get 3 times the absolute value of x minus 2. Everybody agree with that? We're okay with that? Is less than 0.01. Well, what's the last step? Divide by 3, and look what we got. That's what we wanted, right? We wanted to have the absolute value of x minus c. Well, look at that. X minus c, c is 2, magic, is less than delta. That's what we're looking for, is delta. Well, it's just going to be 0.01 divided by 3. How about that, right? So absolute value of x minus 2 is less than 0.01 over 3, just a number. Okay, so that's how narrow our neighborhood would have to be, right? It'd be less than that in order for us to get this target accuracy for our function, to be within 0.01 of the actual limit, 8. That make sense? So for our y values to be between 7.99 and 8.01, we would have to have an x value that is between, what are we going to get here? 2 plus that and 2 minus that. Okay? Make sense? Pretty good. Okay? we could do one better though. I could change this question and say, and omit all the numbers and just say, prove that it works. Okay? So if that's the case, I don't really care that, well, I pinned it down to a specific number here, didn't I? If I wanted to be completely general, which is always better, I could have just left that as an epsilon. Agreed? Would agree with that? So then this would become instead, this would become the statement, yeah, we'd get the absolute value, oh, that's a horrible color, isn't it? We need something like, what am we using? Green. There we go. Absolute value of f of x minus L is less than epsilon, right? Okay, but we knew what f of x was. We better write this down because I don't have that other screen there. Wasn't f of x 3x plus 2? And c was 2, and we calculated that L was 8, right? Okay? So if we plug that stuff in, this is just going to become the absolute value of 3x plus 2, looks really familiar, minus L, which is 8, okay, is less than epsilon. Well, that's just the absolute value of 3x minus 6 is less than epsilon. If I factor out the 3 and divide by 3, can we just do that in one step, same as before? So absolute value of x minus 2 is less than epsilon over 3, right? Okay, but epsilon over 3 then is my delta, isn't it? Because doesn't this just match the form absolute value of x minus c has to be less than delta? Well, look what we did. This is pretty subtle, but super cool. We made a connection here. We said that delta is in fact related to epsilon for that function. There's our proof. Does it matter what we pick epsilon to be? Doesn't make any difference. That just tells me that my corresponding delta is 1/3 of the epsilon, right? So didn't we just prove that this works, right? We can get arbitrarily close to L, right? So we can shrink our epsilon down to as small as we want to by just restricting our delta in a predictable way, right? That relationship is never going to go away for that function, right? We know that the limiting factor here is we can make epsilon arbitrarily small. Delta just has to be smaller than that expression, right? Does that make sense? That is possibly conceptually one of the hardest concepts that you could find in first year calculus, I think. Because it's, no, really it is. It really is because it's so arbitrary. I mean, there's so much, right? I mean, it's a pretty subtle relationship. These are weird proofs. It's a weird proof we just did, but it worked because we got a connection, right? Now, this wouldn't work if our answer ended up being something like, I gotta think fast here, let's see, what if delta was something like 3 over epsilon? That wouldn't work, how come? Yeah, because now as epsilon gets smaller, delta's getting bigger, right? You get the idea? Yeah, so that wouldn't work, right? That couldn't. What kind of function would do that? Not a function that has a limit, right? The further you get away from C, the closer you're getting to the limit? No.
What kind of function would do that?
Well,
400,
Not
really.
good.
I mean, ready, let's do it. We got 2 minutes.
well, I mean, honestly, if I had to, I would say probably a function like this, something that was going,
Oh, back to the asymptotes.
yeah, right? As I get closer and closer and closer, I get further apart, but as I get, maybe these things both, like these are both asymptotic on the x-axis, right? See what I'm saying?
Yeah.
So if I go further in that direction, I approach a y value of 0, further in that direction, but that's not a limit, is it? Right? It didn't work.
But it is a limit, it's just infinite.
Well, no, it doesn't work as a limit. It doesn't work as a limit because as x approaches 0, right, it's not a finite limit, as x approaches 0, we don't get some predicted value. Right, there isn't.
Oh, yeah.
See what I'm saying?
Yeah.
So that doesn't work. If I flip it around, it did work though, because then as epsilon gets smaller, so does delta, right? These two intervals are going to shrink in concert, which is what they have to do for it to be a limit. As this gets smaller, this must get smaller, right?
So they can't be inversely related.
So they could not be inversely related, right?
But couldn't you still, have a limit on an asymptotic function, just not at that certain spot, but if you needed it to be like x equals.
Well, yeah, would that be a different limit?
Yeah.
Yeah.
Okay.
Yeah, we could have had a limit at negative infinity, but that's not what we were talking about.
Right,
Yeah.
okay.
Okay? Sort of, kind of, maybe, get the idea?
Awesome.
Yeah, it's cool stuff. Don't worry, I'm not gonna throw a bunch, I mean,
So it just gets easier from here, right?
oh yeah, that issue, just to kind of put this in perspective, what we just did today, looking at the formal definition of a limit, you never do. You always just use the informal definition that we've been using, okay? So.
I don't know what that means, it's gonna be easier from here.